Hello friends, it's day 22 of the advent of compiler optimization, and we're changing tack and we're going to look at some cool and interesting things that I noticed Clang does when it's looking at comparisons of strings. So I'm going to use a string view here, and I'm going to write a series of routines that check whether a string view that's being passed in is equal to a particular string. In fact, I'll just write one routine and we'll keep changing it. You can see the kind of things that the compiler does. So let's do, is token. So we're given a string view, SV, and then first of all, let's say, what if we compared with the empty string? What do you think it's going to generate? So over here, if you remember, a string view is a pointer to the string and the size in characters of that string as a little structure that's being passed by value. And on the Linux ABI, we will see those value and pointer being passed in two registers. Now, it just so happens that the length is the first element of the structure, which is sort of counterintuitive. At least it is in the GCC implementation of string views. So what we'll see is RDI is the length and then RSI is the pointer. So here in isToken, checking it to be an empty string, it's just checking to see if the length is 0. So testing RDI with RDI, and if it's 0, then AL will be set. So set E is set if equal AL. AL is the low 8 bits of the A register, the EAX, RAX register, that kind of thing. And so what we're doing here is we're saying, if it's equal to 0, return 1, else return 0. Easy. No string comparisons done at all. Fabulous. Very clever. What if it was a single character? Let's do just a capital A. There's going to be a theme in all of these versions. The first thing we're always going to see is that it is going to... Oops, come on, get away. It's going to be comparing the length of the string on the right-hand side. Now, you'll notice that I'm not comparing it with a string view. I'm actually comparing it with a string literal on the right-hand side here. But behind the scenes, the compiler knows how long this string is, and so it's already worked out all of the things about it. I originally did this by making a string of A, or using the SV suffix to force the right-hand side to be a string view, but it turns out the compiler can use the constructors for the string view and sort of context reevaluate them already, and so it knows that the length on the right-hand side is 1. And so it's comparing to see whether or not it's 1. If it's not, then we just return false. Otherwise, we compare the one and only byte that we care about with the capital A. So far, so good. Makes sense. As the string gets longer, we'll see something interesting happen. So for 2 bytes, now we're comparing the word pointer, which is the 16-bit value in x86 land, with this value, which is hex 4241, which is AB packed together. ABC, well, now we don't have a 3-byte read. So here we check for it being 3 characters long, then we check the first value, if it's AB, where are we? Yeah, AB. And then we check the last value if it's C. Now, the interesting thing here is the compiler hasn't used a whole bunch of jumps. It is, you might otherwise expect that it say, well, let's check if the first 2 are AB, then carry on, else go to fail, and then check C. Instead, what it's doing, and this is Clang, is it's reading in the 2 values, exclusive ORing them with the value that we're trying to compare with, and then ORing the result of that together. So, as we learned on the very first day, exclusive ORing a value with itself returns 0. We then OR those 2 registers together, which means that if any bit in either of them is set, the value will be non-zero. And then we say set if equal to 0 in this instance, AL. So that means if any bit was set at all, then we will return false, but only if all the bits were 0 will we return true. And the only way the bits can all be 0 is that we read AB and then C, because the XORs matched and got 0 in both cases, then we ORed them together. Pretty cool, eh? And as we make the string longer, we see it goes through various other iterations of this trick. At 4, we will just compare the 4 bytes with a 4-byte read instruction. At 5, we will read 4 bytes and XOR them, and then read the 5th bit and XOR them. And then something I've noticed that's really cute is if we have 7, so we're going to do A, B, C, D, E, F, G for 7 bytes. Here, we're seeing that it reads 2 4-byte regions. So it's comparing RSI, the 4 bytes at RSI, with the 4 bytes at RSI plus 3. Now, those overlap. So it's actually comparing like 4 and then 4 like that. And so the first one it's comparing with A, B, C, D. And with the second lot, it's comparing with D, E, F, G. And that just saves a whole bunch of other comparisons. And it doesn't matter that we're comparing the D version twice. It doesn't matter that we're comparing the D value twice. We still get the same answer. So that's a really neat set of tricks that Clang pulls out for comparing these values. And it obviously applies to anything where Clang can generate a sequence of comparisons like this. So it's just a whole bunch of neat tricks that I've noticed along the way that Clang does for comparing things. This was a little bit of a lighter episode, but hopefully you enjoyed it, and I'll see you tomorrow.